on science and religion, I'd like to lead off with this quote by C.S. Lewis: "Don't base your faith on science, because science will change, and then there goes your faith. Base it on something else." That being said, this is really interesting stuff, and if my clicker works, it does. Most of us here in this room are probably old enough to remember this famous Time magazine cover from 1966. Is God dead? And there have been a lot of discoveries since they printed that cover in 66, and contrary to popular belief, virtually all those scientific discoveries are going in the opposite direction of what that cover says. God is not dead, very much alive. Mentioned these two books previously in the talks that I've done. Highly recommend you pick up a copy if you're interested at all. They talk about largely the same topics: the Big Bang, the Goldilocks universe, the DNA enigma, which is what we're going to talk about the next 2 Sundays. Stephen Meyer's book is very scientific. He's a PhD scientist. It can get deep. But Eric Metaxas's book is very accessible and worth picking up and reading. Eric Metaxas also has a video series called Socrates in the City, where he interviews a lot of the people that he talks about in the book. So, with that as background, and we're going to talk about evolution. The way we've heard of it in school and in popular culture, it's all about Darwin and natural selection. Something we all observe is that organisms have differing traits. Some traits are more favorable to survival than others, so the population tends to acquire those traits, and the population changes over time. Random mutation creates these new traits. In Darwin's time, they really didn't know what caused the mutation. They just noticed that it happened. Natural selection preserves the traits and passes them on to the next generation. For those of you who have a literary bent, think of mutation as the writer, natural selection as the editor of what stays. Over time, favorable traits, as I said, stay in the population. You have 2 kinds of evolution: microevolution, changes within a species, and then macroevolution, where one species changes into another. He published his paper in 1959, as you see on the screen, and it made some big claims, and it was controversial. One of the big claims was that all life on Earth derived from a common ancestor, a single cell somewhere, in that the cumulative effect of tiny, tiny variations over a long period of time would create everything we see today, all the different animals and vegetation and everything. Darwin's work was combined in the late 1880s with the work of an Austrian geneticist named Mendel, and they determined that something called genes were what created change and mutations. They still didn't totally understand them, but they knew that they happened in genes. The theory, as you would imagine, was enormously controversial in its time, and in 1860, the year after it was published, there was a big debate at Oxford. One team of debaters was led by Bishop Wilberforce, who's William Wilberforce's son, and the other team by a guy named Thomas Huxley, who was known as Darwin's bulldog. He was just a really vicious defender of evolution. If you look at what both sides wrote after that debate, each side thought they had won the debate, but if we look back over the last 150 years, I mean, it's kind of clear that Huxley's argument carried the day, and evolution is predominant in our culture. Something that arose out of that debate is something called the infinite monkey parable, and we've probably all heard one version or another of this, that if a million monkeys sat down at a million typewriters for a million years randomly banging out letters, they had eventually produced the works of Shakespeare. This was incorrectly attributed to Huxley. He actually used a different monkey story there, but it has carried on, and it's prevalent in the culture. If you look back at the infinite monkey theorem, the whole concept turns out to be very ancient in origin. You can find references to something like this in Aristotle and Cicero. In one of Cicero's works, he mentioned if you just threw random letters on the floor enough times, they would eventually spell a word. It's like, you had your Scrabble letters and you're tossing them, they're eventually going to make a word. During the Enlightenment in the 1600s, you had a mathematician, Blaise Pascal, mentioned it. Jonathan Swift also mentioned it. It is a really common argument that you hear in evolution debates in modern times. It's also part of popular culture. Bob Newhart has done a comedy skit on it. Those of you who are fans of The Simpsons, they have a whole episode about it. Sci-fi fans, Doctor Who has done a whole episode, and there's many other examples of this. It's kind of pervasive. When you find it used in modern days in an evolution discussion, it's rarely used to further the discussion. It's used to shut down the discussion. Somebody in favor of evolution and the power of gradual change over time will say it, and then they do a mic drop like they've said something profound. I'm here to tell you it's really not profound, and if you hear that, you shouldn't be shy about challenging that, and we're going to get into that in a minute. Back in Darwin's time, when he created his theory, the smallest unit of life they knew of was the single cell. And it was kind of like the picture in that upper left-hand corner. There was a cell membrane, there's a cell nucleus, and there's a blob of protoplasm in the middle, and that's all there is to it. We have subsequently found out in our modern day and age that cells are infinitely more complex than that simple picture that Darwin had at hand. If you looked inside the cell and blew it up to the size of a modern city, you would see there are individual structures inside the cell that act like FedEx drivers, driving other things to and fro. There are other parts of the cell that are manufacturing things so the cell can live, but it's incredibly complex. And Darwin, and really up until the 1950s, nobody had an inkling of how complex the cell was. Come on. Oh no. There we go. And what happened in the 1950s? In 1953, a couple of British scientists, the name of Watson and Crick, they discovered the molecular structure of DNA. They got the Nobel Prize for this discovery, and this opened up a whole new world of insight into microbiology. After they discovered this, genes were no longer some abstract thing that they didn't know about. It's like we know where they are, we know their structure, and we understand that genes correspond to very long sequences of DNA molecules. Crick went on in 1957 to develop theory on top of the structure of DNA he called the central dogma of molecular biology. And it dealt with the flow of information inside of a cell, that information flowed from DNA to RNA to mRNA to amino acids, then to protein. What do we mean by, information in DNA? That was a strange concept to me when I first heard of it. And here's what it means. There are 4 chemical nucleotide bases involved in DNA. Their names are up there. I'll mispronounce them if I said them, but they're commonly referred to by the first letter of each chemical base, A, T, G, and C. And Crick in 1958 came up with his sequence hypothesis that those 4 bases function the same way that the letters in an alphabet function. And that specific sequences together, and by the way, it's not just those 4 letters, it's those 4 letters sometimes duplicated hundreds and hundreds of times in different combinations. They carry information. These different sequences mean you've got red hair versus blonde hair, you're tall or short. Some sequences had meaning, and other sequences are just complete gibberish. This hypothesis was later confirmed by experimentation. But, what are the implications of it, that it behaves like a language? We're all familiar with languages, right? If you analyze languages based on something called information theory, which was another thing discovered in the 1950s by a professor at MIT named Claude Shannon, the reason we understand languages is languages have rules, they have grammar, right? So if you look at the sentence up there, to be or not to be, and then what follows it that I made up with a random number generator, rho not bet boo, those contain the exact same letters, the exact same number of spaces, but one means something, the other one is complete gibberish, means nothing. DNA sequences act the same way. Some sequences mean something, others are complete garbage. Linguists, when they apply information theory to language, if they took, for example, our English alphabet with 26 letters, and you just took 100 of those letters, they've computed that you could create 10 to the 25th power grammatically correct sentences. Now, what's 10 to the 25th? It's a big number, right? Most of us don't deal with exponentials. We're going to get to that in the next slide before we go on. But suffice it to say, that's a lot of sentences you can create with 100 letters. On the other hand, with 26 letters in the alphabet, there are 26 to the 100th power possible combinations of those 26 letters. That is an infinitely bigger number than 10 to the 25th. And the point being, the number of possible sentences that are grammatically correct, even though it's a large number, it's minuscule compared to the possible number of letter combinations. This is going to be an important thing to remember as we go forward with DNA. But first, I want to talk about exponential numbers for a minute. Most of us don't deal with them. If you run into them, you just know it's a really big number. I actually have to deal with them as part of my work from time to time, and although I understand them, I find I truly don't understand the magnitude of them and the magnitude of one as it relates to another. So I thought I'd try to find an example here to kind of give you an idea of the kind of numbers we're talking about by relating it to things we're familiar with. So start with a grain of rice, something small that we've all seen. The average size, length of a grain of rice is about 6 millimeters, average width a little under 3 millimeters. The area that a grain of rice covers is 17¼ square millimeters. Okay, that's something small that we can comprehend. A big number that we're probably all familiar with are the odds of winning Powerball. It's 1 in 292 million, right? Really rotten odds. So, if we wanted to visualize the odds of winning Powerball using grains of rice, it's picking one grain of rice out of 292 million, a rotten bet even for $1, but how much area is covered by 292 million grains of rice? And the answer is on the screen. 292 million grains of rice would cover a football field. I chose the Browns football field in honor of Fred. If you like a different football field, take it up with him afterwards. But the odds of winning Powerball, the odds of picking one grain of rice out of an entire football field covered with rice, terrible odds. The numbers we're talking about when we get into exponentials are far bigger. An illustration of that is the apocryphal story of the Chinese emperor who wanted all of his inventors to invent him the perfect game, and they all went out and worked on it. And one inventor came back to him with the game of chess, and the Chinese emperor loved it so much, he said, "This is the greatest game I've ever seen. I'll pay you anything you want as a reward. You can have half my kingdom. You can have your weight in gold. What do you want?" And the inventor said, "Your Highness, it's very simple. All I would like in payment is for you to put 1 grain of rice on the first square of the chessboard, 2 grains of rice on the second square, 4 on the third square, and keep doubling it all the way through till you fill all 64 squares on the chessboard." And the emperor said, "That's all you want? Sure, let it be done." So, how many grains of rice did the emperor agree to pay? If you do the math, he agreed to pay him 2 times 2 to the 64th minus 1, which is approximately 3.7 times 10 to the 19th grains of rice. Now, we know that 292 million grains of rice cover a football field. How much area does 10 to the 19th grains of rice cover? The answer is it would cover the entire surface of the earth, plus a bunch left over to cover North America, two grains thick, right? It's an enormous amount of rice. That is how big, how quickly, and the first time I heard this, I didn't quite believe it, so I went and built a spreadsheet and calculated it out, and it's right, you know? I mean, it really is. The numbers we're going to talk about here, as far as DNA combinations and the chances of picking one, are far bigger than this 10 to the 19th number. So now that you've kind of got a picture of the kind of numbers we're talking about, before we move to DNA, let's dispose of the monkeys, right? What's the probability that 1 million monkeys really could type the works of Shakespeare in 1 million years? People have actually tried this with real monkeys. As you would expect, nothing happened other than the monkeys broke the typewriters. But in the age of computers, people are constantly simulating this for, you know, whatever reason. When I went out looking on the internet for an example for this week, I got lucky and found Scientific American has just published a paper this month on the very topic. The guy who did it wasn't trying to figure out how long it would take to type, for monkeys to type the works of Shakespeare. He just picked out one sentence: to be or not to be, that is the question. And he calculated it would take almost 10 to the 59th years just to type that one sentence, okay? If you went 10 to the 59th grains of rice, that's like rice covering the earth to a depth of many, many miles thick. And you've got one chance out of all that rice of just getting this one sentence. The universe is only 10 to the 10th years old, for crying out loud. So this is longer by far than the universe has existed. In other words, no, monkeys could never, ever, ever type the works of Shakespeare. And if you ever hear somebody use that on you with a mic drop, tell them to go do the math, because you have, and you know it's not possible. That being said, get serious again. Could evolution have happened the way the Darwinians say, right? If DNA information behaves like language, like Shakespeare, what are the odds that random mutation can find a functional sequence that means something? There are actually some PhD scientists, I've listed them here along with what their PhDs are in, and these distinguished universities, or formerly distinguished in some cases, went to. And the first guy on the list, Murray Eaton, he was actually trying to calculate out how long evolution would have taken, and the numbers weren't coming up right for him. He called his buddy, the second guy on the list. He said, "Could you check my math? This isn't working out the way I thought it would." They ended up calling a conference, and I'm going to read the quote at the bottom, which the conference was kicked off with this statement by Sir Peter Medawar, a Nobel laureate in biology. And he said, "The immediate cause of this conference is a pretty widespread sense of dissatisfaction about what has come to be thought of as the accepted evolutionary theory in the English-speaking world, the so-called neo-Darwinian theory. There are objections made by fellow scientists who feel that in the current theory something is missing. These objections to current neo-Darwinian theory are very widely held among biologists generally, and so we must on no account make light of them. The very fact that we are having this conference is evidence we are not making light of them." When I first read, I had to pause for a second. These are very widely held among biologists. I miss that somehow in the popular culture. We're always inundated that, you know, you're a knuckle-dragging, mouth-breathing Yahoo creationist if you don't believe Darwinian theory. But here, what? Widely held among biologists? That word is not getting out. What they found out at the Wistar conference, they calculated the number of possible combinations of amino acids that would have to be searched through for a random mutation to work, and it came out to about 10 to the 195th power, which is, I have no way to describe that other than to say there are only 10 to the 80th power atoms in the entire universe, so it's a number much bigger than the number of atoms in the universe. How in the world could random mutation, you know, find a valid combination among that many combinations? So although this is the denominator, how many combinations are possible, what the scientists at the conference needed to find out, how many combinations are functional. Maybe it's a really, really big number too. One wit of a biologist made the quote at the bottom that it looks like natural selection may explain the survival of the fittest, but it can't explain the arrival of the fittest. And biologists set to work on that. They needed to come up with new technologies in order to figure this out, and new technologies were invented, needed to be able to make customized synthetic DNA, needed to be able to change site-specific existing DNA. They invented these technologies. These are the wonderful things that also allow you to do other things like gain-of-function research on viruses, which is a different story altogether. A biologist in the 80s named Robert Sauer did some of the first serious work here at figuring out the number of functional combinations, and it turned out to be a very big number, 10 to the 132nd, which is a huge number of functional combinations, but he didn't emphasize the ratio. 10 to the 132nd divided by 10 to the 195th still means you only got a 1 in 10 to the 63rd chance of finding one that works. Pretty bad odds. His work was expanded upon by a chemical engineer PhD from Caltech, who later did his postgraduate work at the MRC Center, which is the same place Watson and Crick worked to discover DNA in the first place, and he established that the probability of finding a functional combination in random mutation in search is 1 out of 10 to the 77th, which is essentially 0. You know, it didn't happen the way they said it's going to happen. They said it happened. It's the same odds as Shakespeare's monkeys creating, or the monkeys creating Shakespeare. The probability is 0. So, how long has all this been known? The Wistar conference, where they first questioned things, happened in 1966, the same year Time magazine published that famous magazine cover. You don't hear about it, right? Robert Sauer did his work, published it in peer-reviewed magazines in 1990. You don't hear about it. Douglas Axe published in 2004, 20 years ago. You don't hear about it unless you're looking in the right places. Somehow, it's almost like there's a deliberate movement trying to suppress some of this information. What's been the reaction to some of this? And this is an eye chart. I'm going to read some of it for you. But some scientists, took the scientific approach. They said, we're going to look at the math here, or we're going to try to modify Darwinian theory to see if we can come up with something that does work with these numbers. Hasn't been anything successful so far. Much more prevalent is you see unscientific responses, ad hominem attacks, silence. In one egregious case, the publisher of one of the peer-reviewed magazines on the previous slide, a guy who has 2 PhDs in biology, got fired from his job for publishing such a heretical paper. Not the response you're looking for from serious scientists. Another PhD, a guy named David Galertner, he's a PhD in computer science, not biology. He published an article in 2019 called Giving Up on Darwin. And I'm going to read some of the quotes that he said. He said, "Like so many others, I grew up with Darwin's theory and had always believed it was true. I had heard doubts over the years from some well-informed, sometimes brilliant people, but I had my hands full cultivating my garden, and it was easier to let biology take care of itself. But in recent years, reading and discussion have shut that road down for good." And he published this article, and he really got attacked for it. And he said in some interviews later on, "The theory of evolution virtually functions as a religion to some scholars, especially within the scientific fields. As far as they're concerned, you take your life in your hands to challenge it intellectually. They will destroy you if you challenge it. Such extreme allegiance to evolutionary biology fosters a deficit of free speech within academic communities. What I've seen in their behavior intellectually and at colleges across the West is nothing approaching free speech on this topic. It's bitter rejection. It effectively shuts down meaningful scientific intellectual discussion." And that's what's going on, but there are cracks that are showing up, and we'll get into more of those next week. But I want to go back to Crick. Right? He discovered DNA, won the Nobel Prize, super smart guy, and also no respecter of Christianity. He's famous for saying, "I do not respect Christian beliefs. I think they're ridiculous. If we could get rid of them, we could more easily get down to the serious problems of trying to find out what the world is all about. Now, he knew about DNA. He knew the math we just went through. He knew it wasn't possible. But also, he had blocked off the road to a creator. He just can't stomach it. But he needed an answer. So in 1973, he published a paper in a peer-reviewed scientific journal called Icarus. The paper was called Directed Panspermia. In 1981, he doubled down and wrote a book called Life Itself, Its Origins in Nature, about direct panspermia. The technical definition of directed panspermia is the deliberate transport of microorganisms into space to be used as introduced species on other astronomical objects. Translated into English, he proposed that space aliens planted life on Earth, and that's where it came from. And they call you nuts if you believe in a creator. This is how far they're willing to go. It's just not intellectually honest. There's no need to back down to evolutionists when they're pounding on this stuff. They really don't have the science behind them. And there's more and more scientists that are coming around to this view. And next week, we're going to explain to you how this was the easy part. It's even harder than this. And we'll talk about that next week in building a better mousetrap. If anybody wants copies of these slides, Dan's got them outside. And I'm happy to talk to anybody afterwards, but we'll continue with the service.